This is page 3, starting with problem number 26 for the grade 7 advanced post-course test. And it starts off, you collect data about the number of hours spent studying, X, and the test scores, Y, for several students. An equation of the line of fit for the data is y equals 5x plus 61. Interpret the slope and the y-intercept. So number of hours. So x equals the number of hours studying. So x is studying, y is your score. Okay, the scores for students. So if we plug in 0 for that equation, so we have y equals 5 times 0 plus 61. So if we study for 0 hours, the score I will get on my test is a 61. Okay, got it. So what if I study for 1 hour? What is my score now going to be? Well, if I study for an hour, I get 5 points plus the baseline, which is 61. So 1 hour gets me 66, a score of 66. And then if I do 2, you see what's going to happen. 2 times 5 is 10. So for every hour I increase, I get 5 more points. So that's going to be 71. And so that is what this is. So the slope, it says, what is the slope? The slope is 5. The slope represents the number of points per hour that I get in addition to my baseline, which is my y-intercept. So I'm going to start at a baseline of 61 points on the test, and then for every hour that I study, I will add 5 points to that. So that's how we interpret this. I don't think we have to graph it, and I think that's all they want to know. So very interesting, really, really important skill to be able to understand how these terms, this is a term and this is a term, how it affects the total and how those increments go. And as we see, we're adding 5, and we could just keep going. All right. Number 27 says you randomly survey middle school students and high school students about whether they prefer baseball or soccer. The results are shown in the tables. Create a two-way table that includes the marginal frequencies. So a two-way table, as you see here, so I pulled this information, a two-way table with marginal frequencies in Big Ideas Math. So marginal frequencies. So what we do is we're just creating two types of totals and information, two-way info. So what we have here is we're going to have our two categories, right? Baseball, soccer. So we have baseball and we have soccer as our categories, and then we'll have a total underneath that. And then, so that goes this way. And then we have middle school and high school as our other categories. So middle school, high school, and then total on this one also. So baseball for middle school is 60. Let's do it in a different color so we can see that. So baseball is 60 for middle school, 25 for soccer, which gives us 85 for total. High school is 66 for baseball and 51 for soccer, which gives us 117. And then you have to total these up. So that's going to give you 126. That's going to give you 76. And notice if we add these two together and add these two together, we better get the same total. So that's 12, that's 10, 202, and if we add these two, that's 12, and that's 20, So 202, and that's the important component. That little note, the sum of the total row should always equal the sum of the total column. And these sums represents the total number of observations in the survey. So those sum represents the total number of students. Cool? Yeah, that's neat. So that's called a two-way table because we can read it two ways. And then the marginal frequencies are these. That's how frequent it happens. Do the ordered pairs 2, 20, 5, 15, 12, 19, 14, 13 represent a function? Okay, so what we do is we want to, well, we could graph it. That's number one. Number two, we could also look, and we're looking at our inputs and our outputs. For every input, there needs to be one unique output. So when we input 2, we're always going to expect to get 20. We can't input 2 and get 21 time and then input 2 and get a different value. That would not be a function. So since none of these values repeat, or inputs repeat, this is input, comma, output. We call it domain, comma, range. Also, you can call it independent, comma, dependent, because the dependent variable is dependent on what you input, or the independent. So those are the reasons why this is considered a function. So, and remember, we use the vertical line test. So you take a vertical line and you drag it, and there should only be 1 point on the graph. Graph the function y equals negative 5/4 x plus 2. So we went over this in page 2, that there are 3 different linear equations. So linear equations. Examples or linear equations are slope-intercept form. And slope-intercept form is y equals mx plus b. We have standard form. Standard form is ax plus by equals c. And none of these values represent anything. This is the slope. This is the y-intercept. In standard form, nothing is represented by these variables outside of x and y are coordinates, and x and y are a point or a solution also. But we find, what we do, we find the x and y intercepts when it's in standard form. And then the last form is point slope, and you can decipher it from the name point slope. You're going to pull out a point and the slope, and the equation is this: y minus y sub 1 equals m times 20 x minus x sub 1. So m is the slope again, and you have x sub 1, y sub 1, which is a point. And then this x and y also is another point if you have 2. So we want to graph it. So it's in slope-intercept form, so I'm going to be able to utilize the slope in the y-intercept. So the slope is going to be negative 5/4. The y-intercept is 2. We always graph the y-intercept first. We're going to make a dot, and then we're going to use the slope. The slope is negative 5/4. That negative can go on the top, or it can go in the bottom. It doesn't matter. We would rise 5 and then run, or go left because it's negative 4. And then if we had the negative up on the top, you would go down, rise. That would be up, Mr. Mac. Rise, up 5. That's up 5, left 4, or we go down 5. Positive 4 is right 4. And we'll see. So from this point, we can go up 5, 1, 2, 3, 4, 5, and then left 4, 1, 2, 3, 4. Up 5, 1, 2, 3, 4, 5, left 4, 1, 2, 3, 4. So that's there. And then if we go from this point and use the other slope, we would go down 5, 1, 2, 3, 4, 5, and right 4, 1, 2, 3, 4. down 1, 2, 3, 4, 5, 1, 2, 3, 4. And notice it stayed on the same linear path. So we notice that it doesn't matter which version of the slope we use, it's always going to take us along that same path. And when we graph, we always have to use arrows. And we typically want 3 points, at least a minimum. And that's how you graph the function y equals negative 5/4 x plus 2. We know negative slopes are always going to go down left to right. Positive slopes are always going to go up left to right. Zero slope is a horizontal, and no slope is a vertical. Two arcades charge an entrance fee and a fee per game. At Arcade A, the total cost, y in dollars, of playing X games is represented by the linear function y equals 0.75x plus 5. So this is going to be the number of games. This is going to be games. This is going to represent the cost per game. This is going to represent my entrance fee. And this is my total cost. Okay, deciphering that from that. The table shows the total cost for playing X games at Arcade B. Which arcade has a higher fee per game? Well, if you play 0 games, it costs you $8. Okay, that's how much it costs to enter. And then we want to see, okay, number of games is 4. So we have a, well, we can do, let's write an equation. Sorry, I meant to erase it. So let's take this. We'll see how we can write a formula for this. So we'll use y equals mx plus b. And so remember, if we plug in, my b is my y-intercept. Y-intercept always is when x equals 0. So I know my b is 8. So I can fill in this formula, part of the formula, and then I have a point. I have 410, so 10 equals m times 4 plus 8. And this allows me to find that rate of games. So I'm going to subtract 8. That leaves me 2 equals 4m. I put the coefficient in front of the variable. I'm going to divide by 4, and I get 1/2 equals m. So that's the cost per game. It's in the same location. M in this example is the cost per game. B is the entrance fee. So it costs me 50 cents per game. So first question, which arcade has the higher fee per game? That would be A. That would be Arcade A. And then Arcade B is going to have the higher entrance fee because that's $8 to get in, and this is 5. So this is entrance. This is game. And that's it. So A for the first question, B for the second question. Good questions. Determine whether each equation represents a non-linear function. So this is a linear function. Y equals mx plus b. This is non-linear. This is y equals ax squared. You can also get that, which is y equals ax cubed. And you can get different ones. So those are nonlinear. Since this equation will simplify to 5x plus 5, that is going to be a linear function. So it is not, how would we want that? Yeah, no, it is not nonlinear. It is linear. This is not only squared, but it's in the denominator. So those are two bad things. And bad things meaning to linear, so this is a nonlinear. This is nonlinear. This is something, I think this is sort of, it's negative, so I bet you it's something like this. I think that would give me, let's take a peek and look on Desmos real quick. So let's throw that in. Always fun to, oh no, Desmos, huh? No, Desmos. That's interesting what it probably took me to. It's not probably a good place. It is negative, what is it? Negative 4 over x squared. Oh, okay, it was close. I just forgot to invert it. I forgot squared. They're going to be in the same quadrant. So close. We would. So this is actually over here. Yeah, and it's going to be inverted. So we can take a picture of that. And so that would be considered nonlinear. Desmos is great. Utilize it. It's always good assistance. It's good to use. You learn, and it definitely gives you some experience, and you can reference it. Also, okay, so now this is a parabola. So this will give us a parabola that is shifted up 6. So 1, 2, 3, 4, 5, 6. It's the parent because it doesn't have a coefficient, so it looks like that. So that is nonlinear. Yes, nonlinear. And if we go in there and take it on Desmos, y equals, what is it, 6? Oh no, x squared plus 6 raises it up 6. Yep. And if we look at it like that, that looks just like my graph. Yep. So that's helpful. We'll paste it. It's very interesting that it's constantly not allowing me to pull. Okay, next one. This is the parent of it. This is the true one. It is a traditional parabola, so yes, also nonlinear. We won't have to do Desmos because we know. Number 32, create a graph for each situation. The temperature increases slowly at first and then more quickly. So when you have a chart like this, so over time you have temperature on your y-axis, you have time on your x-axis. So as you go, the temperature is going to increase slowly and then it jumps. Okay, so it's going up faster in a shorter amount of time. That would be A. The temperature decreases at a constant rate. So decreasing at a constant rate would just be a linear line. So that's not going to change. It's going to be a straight line decreasing. And again, this is over time as time is 0 to more time. And this is your temp. And your temperature starts here and it decreases at a constant rate. Simplify the expression, write your answer as a power. So when we have like bases and we're multiplying like bases, exponents with like bases, so this is like 4 times 4 times 4 times 4 times 4 times 4 times 4. And as you can assume, there are 5 plus 2 more makes 4 to the 7th. So when we see this, we multiply like bases, we add their exponents because we're taking these 5 and adding 2 more that are all multiplying. When we have a power of a power, so we have 7 of these. So this is my exponent, this is my exponent, and this is my base. So it's this. I have 7 of these. So in actuality, it looks like this. 2, 3, 4, 5, 6, 7. So how many do I have multiplying? Well, I have 2, 4, 6, 8, 10, 12, 14. That's 2 to the 14th. So when we have a power of a power, you are going to multiply their exponents. and you get 2 to the 14. And there are 2 in each of those, right? It's 2 times 2 times 2 times 2, all the way to 14 of them. Xy to the 4th, we have 4 of these. Xy times xy, 3, 4. So we have x to the 4th, because we have x times x times x times x. And then we have y times 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 y. So we have y to the 4th. So that is x to the 4th, y to the 4th. And when we have a power of a power, we can distribute to each of the terms. So that's x to the 1 times 4 times y to the 1 times 4. That's to the first power. You don't see the ones. So that's why we get x to the 4th, y to the 4th. Now when we divide, so 5 to the 8th is 2, 3, 4, 5, 6, 7, 8 over 1, 2, 3, 4. And as we would assume, these would cancel to make 1, these would cancel to make 1, these would cancel to make 1, and these would cancel to make 1, and we'd end up with 5 to the 4th. Well, we see that the 4 of these are canceling with 4 of the 8th in the numerator. So when we divide like bases, we are going to subtract their exponents, and that's 5 to the 4th. Evaluate the expression. Again, we have 2 to the 6th over 2 to the 7th, which equals 2 to the 6 minus 7, or 2 to the negative 1. Now, that's interesting. We have a negative exponent. Do you see why it would end up being negative and what that negative represents? How many do we have in the numerator? 6. How many do we have in the denominator? 7. So we actually have more 2's in the denominator. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So again, we see what's happening with these, and what do we end up with? 1 over 2. So this negative 1 says, hey, we've got 2 to the 1st. It's just in the denominator. These are equivalent to each other. They're just different ways of writing the exponent. The exponent is in the numerator. The exponent is in the denominator. The population of country A is about 12,402,000, and the population of country B is about 1,216,000,000. Approximately how many times greater is the population of country B than the population of country A? So how much bigger is it from each of these? Well, what we do is we divide. We divide 1,216,000, comma 000, and we divide it into 12, comma 406, comma 0, not 6, 2, 0, 0. So let's turn this into scientific notation. So my decimal is right here at the moment, and I'm going to move it until that number is between 1 and 10. So right now it is 121,600,000. Now it's 100 something. I don't know. We just keep moving it. So we're going to move it 1, 2, 3, 4, 5, 6, 7, 8. Now it's 12.169. So if we move it 9 places, we would write it in scientific notation times 10, and those 9 places get represented by base 10 because each decimal place is worth 10. And then we divide it by, we're going to move this decimal point. It starts here. We go 1, 2, 3, 4, 5, 6, 7. Now it is between 1 and 10, so 1.2402 times 10 to the, what do we say, 367. Okay, when we divide scientific notation, we're going to divide the coefficients, we're going to divide the numbers, and we're going to see what we get. And we can use a calculator for this just for purposes to help us simplify. So 1.216 divided by 1.2402 gives me 0.980. 0.980. Whoa. So that gives us 0.980. And now we're going to do the exponents. And we have like bases that we're dividing. So we're going to subtract those. So that equals times 10 to the 9 minus 7, 0.9804. We'll just, is it 4? Do we round the 4 up? 4 would become 5. So actually, 4 is a 5 because there's an 8 after it. Times 10 to the 9 minus 7 is 2. Now this is not between 1 and 10, so we have to move it to the right. We're making a smaller number bigger. Times 10. Now if I move it that way, I'm going to lose a place value. So it's actually 9.805 times 10 would be my answer I would give in scientific notation. 38. Oh, sorry. So times 10 is 98. So approximately 98 times bigger. Sorry. I just was using scientific notation. That's just a little bit easier. So it's about 90. And if we want to approximate, yeah, I guess you could say 100 times bigger. Sorry about that. Forgot the question. Write the number in scientific notation. So my decimal point starts there. 1, 2, 3. It's 231. It's not between 1 and 10. It's 23.1. Now it's 2.31 times 10. And I moved 1, 2, 3, 4, 5 times. So where did that bigness go? I took a big number and made it small. Well, it still needs to equal it. So where did the big go? Well, 10 to the 5th is a big number. And that's where the big went. So important that you understand how and what the representation of scientific notation helps you with. All right, hopefully you did well on those. Those were important 7th grade questions. Have a good one.